welcome guys to the third session of VSSP. This is organized by Curryleaf, which is Alumni Association of MTTS students. And these sessions will be streamed on the YouTube channel of Curryleaf on Curryleaf Days. And without further delay, I would like to invite today's chairperson, Mr. Dr. Kiran Kumar Bera from ISC Bangalore.
Yeah, thanks, Shreyas. And I welcome you all to the third session. I'm quite happy with the turnout. So again, like I said, even though it's a India-Pakistan match today, so many of you are preferring this over the match. Okay, so let's begin. The first speaker for today's session is Joson Henriques. I hope I pronounced it right. And he's from ISER Pune, and he attended level 1 in 2022 main camp, and he will talk on Furstenberg's proof for infinitude of primes. Yes, Josh.
So my topic for today is Furstenberg's proof for infinitude of primes. So as we all know, a prime number is a 1 which has no divisor other than 1 or itself, and it is proved that there are infinitely many primes. The proof that most of us are familiar with is Euclid's proof for infinitude of primes. But this proof that which we'll be discussing today is a more recent one given by Martires Furstenberg. So it's a topological proof, as in we use some special sets to define a topology on the set of integers, and we use that to prove that there are infinitely many primes. So to begin with, we will start with some special subsets of Z, which are these SABs, and we plan to play around a little bit with these subsets and explore some of their properties, which we shall then use later in the proof. So we have defined SABs as the set of all integers of this form, a plus nb. So we fix some particular integers a and b, and you consider all integers of this form, a plus nb. So if you write out the set explicitly, it looks something like this. So you have a plus b, a plus 2b, and so on. And on the left, it extends as a minus b, a minus 2b, and so on. But all of this depends on the a and b that you choose at the start. So you first make a choice for a and b, and depending on the a and b that you choose, you expand this set SAB. So just a few questions first, so that we can learn more about these subsets of Z. Firstly, we should know whether SAB always has an element. So can SAB ever be empty? So the answer to this is no, right? Because regardless of whatever B value you choose, A will always be in the set. B could be, so a B value could be such, as we will explore later, a B value could be such that it might cause some other nice things to happen in the set. But regardless of whatever your B value is, A is always there in the set. So the second thing we try to see is whether this set of SABs, whether it is a finite set, so or whether it's always infinite. So as you see from this description that is given over here, one might think that it is always an infinite set. But if you choose B to be something like 0, then you can kill this this progression on both ends, and a plus b, a plus 2b, and everything will all essentially be 0. Same thing for everything on this side, and you will have only A in the set. So the first observation that we make is that for these sets of this type for SAB, we either have the set to be an infinite set, or the set is just singleton A. In the case of B, so B equals 0. So if we choose B to be equal to 0, then we saw that this progression on both ends terminates, and you have just A left. And in that case, SAB is a finite set. So in some sort, this looks like an arithmetic progression, as in you have a first, like in arithmetic progression, we had a first term. and a common difference. So it is somewhat that, but there is no first term as such that you can consider because it extends infinitely in the left side direction as well. So we try to explore now some special cases of these SABs. Like what happens when B is 0 is what we already saw, that when B is 0, the whole SAB is just a singleton set A. Now what happens when A is 0? So when A is 0, if you look at this set, it is the collection of all NBs. So that if you consider all the collection of all NBs, that can be regarded as just BZ because it is all the multiples of B. And if you actually this set has more structure than just being a subset of Z. If you observe, BZ is not just a subset, but it's also a subgroup of Z. Essentially, all the subgroups of Z that we have seen are of the form NZ. So BZ in particular is a subgroup of Z. And we will use these properties later in the proof. So it is important to make some of these observations. Now, the other case that we see is what happens when B is 1. If B is 1, if B is 1 over here, then the common difference is 1. So you're essentially including all possible integers that are there. In that case, SAB becomes whole of Z. So some of these cases are not very useful to us. For example, in the proof later, for example, when B is 0, we saw that it would be a singleton set, and when B is 1, we saw that it becomes whole of Z. So some of these cases will not be useful to us later in the proof. So henceforth, we will consider all SABs of this form only, where B is strictly greater than 1. Now, the reason why we ignore these negative ones is because if you consider if B is negative, SAB, then SAB is the same as SA minus of B, because in that case, the progression just goes opposite, right? If you have minus difference, then like SA minus B would be the same as this, but these terms would appear on the right side, and these right side terms would appear on the left side. So we ignore these cases of B being less than 0 or B being equal to 0 because that just gives you a singleton set, and B being equal to 1 because that gives you the whole of Z. So henceforth, when we consider these sets of the form SAB, we will be considering B to be strictly greater than 1. Now, any questions so far? Okay, I guess I'll move on to the next part then. So then we consider what happens when in the case when A is non-zero and B is also non-zero. So now if you go back to the way we have defined SABs, this is A plus the multiples of B, which if you remember from group theory, sets of this form can be written as A plus BZ, right? And now again, A plus BZ also has more of a structure than just being a subset of Z. It is essentially the left coset of this subgroup that we saw earlier. It's the left coset of BZ. So if you consider the union of all such SRBs, where R is between 0 to B, that is essentially the union of all such left cosets, right? You will have 0 plus BZ, 1 plus BZ, dot, 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 up till B minus 1 plus BZ. Yeah, B minus 1 plus BZ. Yes. So, as we have seen that these left cosets actually partition the whole of all of integers. So if you consider this union, then this union becomes the whole of integers. Yeah. So, but if we want to see, like, our proof is essentially about primes. So in a short while, we will consider the cases when these SABs involves terms where one of these two integers will be prime numbers. Before that, one little observation that we make is, if an element belongs to SAB, then SXB is the same as SAB. Now, this is again easy to prove because we have started to view these SABs as cosets. So if X belongs to A plus BZ, then we know X minus A is in BZ. And if X minus A is in BZ, then both of these left cosets, X plus BZ and A plus BZ, are same. And the reverse way of proof also follows from the same arguments written backwards. So this is another observation that we make. And then we now start talking about primes. So if you consider S0P, S0P is now, hello? Somebody
Okay.
mic is,
No, carry on, Josh.
yeah. So now we come to the case where these are primes now. So up till now we were considering SABs for just any random integers, but now we look at these S0Ps. So essentially, if you go back to what we discussed, whenever A is 0, these are just PZs, which are subgroups of Z. And not just that, I mean, if you consider the union of these, that is all these subgroups which are multiples of primes, the union, if we talk about this union, intuitively this can be thought of as all those integers which have some prime divisor. And as we know from the fundamental theorem of arithmetic, any integer except 1 and -1 can be written as a product of primes. So this union would be the whole of Z minus 1 and -1. Yeah. So yeah, so now a quick review of all the properties that we have seen of SAB so far, and then we will talk about more of the topological aspects of this proof. So we first saw that SAB can never be empty, as in A, the initial element will always be there in this collection of SABs. Secondly, we saw that SABs are either singletons or infinite sets. But as we saw later, we are not so interested in this proof in the case when this is a singleton set. So we ignore the case of B being 0. Hence, for us, SABs will always be infinite sets. And we also saw that these SABs have some nice structure to them. As in, when you consider A to be 0, then SABs are subgroups of Z. And when A is non-zero, then these are cosets of left cosets of the subgroup BZ. So now with all of this with us, we start looking at some basic definitions of like topology and a basis, which we will use in this proof. So so what is a topology? So basically, if you have a set X, we consider all possible subsets of X, which is known as the power set of X. Now, a topology is a collection of some members of these subsets. So you collect some members of some special subsets of X, which will satisfy some certain properties. Now, those properties are that the empty set and X. So empty set is a subset of the whole set, so it belongs to the power set. X is a subset of the whole set, so that also belongs to the power set. So these two sets are always there in tau. And so tau is basically a collection of sets. So these two sets are there. And if you consider any members of tau, that is any sets which are there in tau, then their union as a set should also belong to that tau. And the third and last property is that finite included. There are finitely many sets in tau. If you consider any finite collection in tau, then the intersection of that finite collection should be an element in tau. So if you have such a collection, so some special collection of subsets of X, which satisfy these three properties, then X along with these special subsets is called a topological space. And these special subsets are called as open sets. So all the members of this tau, all the subsets that we have collected, we call them as open sets. So just so that we get some idea of what a topology is and how things work here, some questions that we should ask ourselves: can this collection ever be empty? Well, no, right? Because these two sets, that is the empty set and the whole space, always belong to the space, always belong to tau. So this collection of these special sets that we are calling as open sets can never be empty. The collection always has at least these two members. Well, next question is collecting only these two members enough? Can you, if I collect only the empty set and the whole space X, is that more than enough to give a topology? Well, yes, right? Because if you consider the union of any elements over here, and any elements in the sense there are only two elements, so union of phi with X is X, and X belongs to the collection. So the second property is satisfied. And if you consider the intersection, now finite intersection, but again, there are only two elements in this. So if you consider the intersection of these elements, that is empty, and empty again belongs to the collection. So clearly this is one very trivial way of defining a topology on a space. The next question we should ask is, initially we defined tau to be some sub collection of the set of all subsets. So it is a subset of the power set. But can tau actually be equal to power set? Well, yes, right? Because in that case also, phi and x will belong, because phi and x are subsets of the power set. I'm calling tau to be the power set. So hence tau and x belong to tau. That condition is satisfied. Now, if you consider any open sets in tau, the union is again a subset, right? Because it again belongs to the power set. Hence, that would also be in tau. Same thing goes for the third property. So this is again another trivial way of giving a topology on the set, that you declare everything to be open. So this is just so that we have some idea of how topology works. I wanted to give out these examples of two topologies. One where you can define a topology by just sticking to the bare minimum. That is, you take only the empty set and the whole set. And the other is the other extreme where you declare everything to be open. Oops, sorry. Yes. Now, very often it so happens that it is difficult to describe all the possible open sets that are there in a space, because you see this collection can have a lot of sets, because clearly, like for example, when you see power set of X itself, you see that if X is infinite, an infinite set, then the power set has a lot of sets. So some special collection that I take might also have a lot of sets, and sometimes it might not be possible to define all these subsets which I want to call as open. So we need to have some nice simpler condition to define these open sets, and that's where the concept of bases comes in. So we define now we define a smaller collection of this power set, which we can use to generate a topology. So it's like what we do with bases in linear algebra in some sense. You take the basis vectors and you use the basis vectors to then define, to generate the whole vector space. So the same way we are considering some small subset, and we will use those elements of those sets to generate the whole topology. So a basis is defined as follows. So it is some special collection such that given any member of the set, you can cover it by some basis element. So if you try to draw a picture, this is the space, and you have some point X. Given any point in this space X, you should be able to cover it with some basis element B. That is the first property. This is essentially like what we do in metric spaces with open balls. So we say that a set is open, for instance, when given any point, you should be able to find an open ball contained in that set. So essentially, I mean, this is like a generalization of the same concept. Hence, you can think of it in that sense. The other thing is that if you have some point x which belongs to two basis elements, let's say b1 and b2, then you should be able to find a third basis element which is contained inside both of these basis elements. Something like this. So if this was my first basis element, which was covering the point x, and this is my second basis element covering the point x, so x belongs to both of these basis elements. I was able to find a third basis element which was contained in the intersection of both of them. So yeah, so once you have a basis, you can use to declare some sets as open. So we declare a set to be open given he's able to find a basis element which covers that set and is contained inside that set. So I think here there is one property missing, that this B should also be there in U. Yeah. So this is like what we do in metric spaces, that if we call a set to be open, if given any point x, you can cover it by a basis element, and that basis element should be completely sitting inside your open set. So that's when we call a set to be open. So we are using a smaller collection of bases to define a topology on a set. So now with these basic definitions of topology and basis clear, we finally move to the proof that I intended to give, that is Furstenberg's proof for infinitude of primes. So the idea is that these sets that we saw earlier of SAB, these are now subsets of Z, and using these subsets of Z, we first try to show that this will form a basis, and these basis elements will then give us the topology that we want on the set of integers. So yeah, so our space is now Z. We are working in the space of integers, and we consider this collection of all SABs where A can be any integer and B is strictly greater than 1. And our claim is that this forms a basis for the set of all integers. So yeah, so for that we need to make sure that these sets satisfy these two properties that we stated above. So firstly, we consider any point in the space, we should be able to cover it by some basis element. So any point in the space, our space here is a set of all integers. So if you consider any integer, we should be able to find some SAB such that my integer belongs to that. Now, as we had observed in our first observation, this SAB always contain A. So if I consider any point x, oops, sorry. Yeah. So if I consider any point x, oh, sorry. Yeah. So if I consider any point x, x will always be in SXB, because if you recall, SXB is the set of all those, is that set of progressions, right? X plus b and so on the right, x minus b, x minus 2b and so on the left. So any member can always, any member of Z can always be covered by one of these sets. Hence, the first criteria is satisfied. Now we move on to the second criteria, that if you have some integer which belongs to two basis elements now, so it belongs to SAB as well as SCD, then we should be able to find some member, something like SX, well, not SXY, but let's say SMN, which is contained in both of these and also contains X. So if you look at that one observation that we made, so this means that X is there in both of these, in SAB as well as it's there in SCD. And we had observed that if X is there in this, then this set is the same as SXB, right? We did that coset argument at the start, that X belongs to A plus BZ, therefore X minus A belongs to BZ, therefore X plus BZ would be the same as A plus BZ. So hence, in place of considering this, we consider these sets. Now, this is done only so that you can reduce the number of variables that you have in this case. As you can see here, there are 4 different integers, and I am looking for a common candidate of this sort, which has m and n. But here there are too many variables to deal with. So I'm eliminating 2 of these and I'm making them just x. But even this is not good enough because we still want this second variable to also be fixed. So for that we observe that if you have b divides d, so let's say d divides b. Yeah, if d divides b, then SAB is contained in SAD. Now this is easy to observe, right? Because B will be some multiple of D. So B will be some dk. So if you consider any element over here, that looks like A plus NB. But B is again a multiple of D. So that is A plus A, which is again some integer times D. So this containment is any element is there in SAB, and it is also there in SAD, where D is a multiple of. So instead of considering these two, we can consider X belongs to SXBD. So with this, we have been able to show that that this set of SABs, where we consider B to be greater than 1, they form a basis for the set of all integers. And using this basis, we can give a topology on the set of integers. So now that we have a topology on the set of integers, we use this to arrive at a contradiction if we assume that there are only finitely many primes. So one important observation that we make is that if you consider any set SOP where P is prime, then SOP is clearly open because these are basis elements itself. But not just is it open, but it is also closed. And that is what will help us to arrive at the contradiction for this. At a contradiction when we assume that there are finitely many primes. The reason why this is closed is because Z is the union of all SRPs. This is again something that we saw at the start, right? Because these are essentially cosets. And if you consider all such cosets where R varies between 0 to P, we know that they partition the space of integers. Hence, their union will be the set of all integers. So S0P is essentially one special case of this. So S0P is essentially one member of this collection. So it is Z minus the remaining collection. Now each of these is open and finite union of open is open. So this member here on the left, this member here is open and the complement of open is closed. So S0P is not just open, but it's also closed. So now we assume that, let's suppose that there are only finitely many primes, P1 to Pn. In that case, we had observed that union of all such S0Ps, where P's belong to the set of all prime numbers, is going to be set of all Z minus 1, minus 1, because these are all such integers. So S0P is essentially Pz. So we are taking union of Pz's for all possible primes. So yeah. So we had observed that when we consider this union of Pz, we are considering all possible integers which can be factored into primes. And by fundamental theorem of arithmetic, we know that that is going to be Z minus 1, minus 1. Yeah. So if you consider this union, we are assuming that there are only finitely many primes, right? So this is the same as this finite union. But now the problem with this is that if you take complements on both sides, here you get just 1 and minus 1. And here you'll have to use De Morgan's law to obtain that this is intersection of Z minus S0 Pi's. Now each of these S0 Pi's is closed is what we had observed, right? For any prime P, we observed that S0Ps are both open as well as closed. So S0Pi are closed, which implies Z minus S0Pis are open, and finite intersection of open is open. Therefore, this left side quantity here is open. Hence, 1 comma minus 1 must be open in Z. But that's a contradiction, right? Because we initially observed that these basis elements that we are considering in our topology, these basis elements are always infinite, is what we had observed when B is greater than 1. So when basis elements are themselves infinite, our open sets are nothing but union of these basis elements. So any open set in this topology that we have given to the set of integers should be an infinite set. But what we are getting is a finite set which is open, which is a contradiction. So this contradiction arises because of this wrong assumption that there are only finitely many primes. Hence, there must be infinitely many primes. Yeah, any questions on this proof? Okay, then. So that was Furstenberg's proof for infinitude of primes. And with this, I end my talk. Thank you.
Thank you, Josh. It was really a very, clear, well said, clearly well said, and it's a nice proof. So, any comments? Okay, good. So, if not, let us thank the speaker again. Thank you, Josh.